So hi everyone, my name is Ashik Muhammad, and I am going to teach you the subject power systems. So this is for HIL interview and HIL exam. So I will be covering the lectures according to the syllabus of HIL. Okay. So I will give you a brief introduction about myself. So my name is Ashik Muhammad and I have completed BTech in 2014 from CET Trivandrum, College of Engineering Trivandrum, and I have written GATE 2014, and my All India rank was 57 with a score of 900, and my total mark was 68. So I have joined I almost got interview letter from 10 PSUs in the 2014, like starting from power grid and all the oil companies and everything. So 10 PSUs I got the interview letter, and from all the IITs because my rank was good, so I got interview letter from all the IITs. And I have attended almost 4 to 5 interviews from PSUs and IIT Bombay, IISc Bangalore, and IIT Madras. So I almost attended 7 to 8 interviews in that year, and I have qualified for all the interviews what I have done in that particular. And I have joined IISc Bangalore, Department of EE for an MTech student. Then 2016, I have joined for MTech from 14 to 16. From 16 onwards, I have registered for my PhD, and it is over this year. I am submitting my thesis this year. And my area of interest is power systems and especially transient analysis of power systems. Transient analysis of power systems, and this is my area of interest. And also, I have written IES 2014, Indian Engineering Service. Now it has got changed to ESC. When we were writing, so it was IES. I have cleared IES 2014 also, and but I didn't join there, so I continued my studies in IISc Bangalore as a power systems researcher. Okay, so this is the brief introduction about myself. So you can feel that I have qualified for different PSUs and MTech and everything. So I am a right candidate for you to teach this the subject of power systems. Okay, so I hope everyone will join. Like I really want to have a live session so that I can talk with people, because the classes which I am going to take here is for basically for interviews and for the not exactly like a gate. So it will be good if people join live so that we can have a discussion about the things what we have studied. Okay. So when I was preparing for my gate, long back, almost 7 to 8 years ago, so my teacher always says how do we study, or we have to check how we study, or how we learn. So according to him, there is a slogan in there, and he actually quote that slogan and says the 25% is coming from the teacher. So that means only 25% of things what you have studied coming from the teacher. So next 25% is coming from your friends or the people you discuss with. Okay, so that discussion is very important. So its slogan is like this: Acharya padam adate padam sishya somedaya sa brahmacharya padam kalakramena. So next 25% is basically coming from yourself. Okay, and last 25% is coming from the time. So you work somewhere or something like that, then that 25% will be coming to you. Okay, so that means this 25% which comes from discussion of your friends, your teachers, and other things, very important for a deep knowledge of something. Okay, so by that way, I hope people will join for live classes. You can talk to me like this: your gate things are now over, so you can relax and you can talk about the systems, why it is so and what it is, or like that. So that means it is a good opportunity for you to talk with someone who really worked for almost 6 or 7 years in power systems and electrical engineering. You can talk about the future perspective of electric. Anything what you want, you can talk with me. Okay, so I hope people will join in live session, and I think it is good that some people join so that I will get a feedback. Else it is almost like a monotonous, like in All India Radio. I will just talk to like some a blank screen without any feedback. Okay, I hope some people will join in the next class. Okay, so we can start with our things power system. Okay, so what is basically power system? I hope most of the people have studied power system for the gate. So what is basically power system? So power system, like if you think, because if you think about your daily life, you cannot survive without electricity, right, or power. So power system is basically, from the name itself, you can say that power system is something which is related to power, okay, or which is related to your electricity or your what the things what is coming in your home, okay. So that is basically known as the power systems. Sorry, I'll just write it here. So what is basically a power system? So if you go back to the normal operating of an electricity, how the electricity is coming to your home. So there is something like a generating station, right? Something like a generating station. Okay, there is something like a generating station. From the generating station, the power will be produced, and there is a transmission system. Okay, from the generation station, there's a transmission system is there, and from the transmission system, there will be a distribution system. And this distribution system, then there will be a load. Okay, load systems. Okay. Okay, so load. Okay, I will say all the classifications later. So you can see that a power system consists of different systems. That is, a generating system is there, a transmission system is there, a distribution system is there, and a load system is there. So power system is a study of all these. What is generating, what is transmitting, what is distributing, how everything is occurring. Okay. So the important aspect of a power system class is how. Okay. So how these things are happening, how generating stations are coming, making, how transmission system is making. So it is not about what. You should have this feeling in your mind. So engineering is always about how it is happening, not about what. You just don't like what is a generating station. So that is not the aspect of an engineering. So engineering should be how a generation works. Okay. So you have to think about that way, how a generation. So what is happening inside? Okay, like that. So what is a generation? What is transmission? What is distribution? That is irrelevant for an engineer, because that, like people like Polytechnic or other things, they already know all the things. So our thing is to design how this works. Okay. So generation station, the most of the things are generators. Okay. So about the generator, we study in our electrical machine course. So this thing we'll study in machines course. Then the basic idea of transmission and distribution is studied in power systems. So this is where power systems are there. And loads, we will study in network and power electronics. So most of the loads are power electronic loads, like new generation loads are power electronics. So these things we will study in power electronics and network. So how the loads are connected, that we will study in the network. Okay. So here, so as soon as the generator generates the power, that power has to be reached from the generating station. It has to reach to the load. So this process of both transmission and distribution is covered under power system. Okay. So if someone asks what is basically a power system, or what are the things what we are going to study in a power system, so that then we have to explain like this. So the power generated in a generating station has to be transmitted and distributed economically. Has to be transmitted and distributed economically and reliably. Okay. So these two things are very important. The power generated in a generation station has to reach the load economically and reliably. Okay. So if that is going to happen, then or how this is going to happen. So that is basically the meaning of a power systems. Okay. So power system basically what it do is it studies the economic and reliable dispatch of power from the generation station to the load. This is the area where we are going to study, and I will be explaining the syllabus according to this in a in a later slide, okay, or in a later of this class. So I hope you understood what is basically a power system. Power system is the process, or it is the systems which reliable, which converts, which transmits generated power reliably and economically to the load. Okay, so this is where the power system works. Okay, so I hope you understood what is basically the thing with a power system. Okay, so if you can have some doubts or something, you can actually contact me. So my number is, I will give you my mail ID. You can contact in this mail. We can have a talk about anything what you like. So this is basically a power system. So we will be covering the generating, a small amount of generating. The theory of the generation is already covered in the machines. I'm not going to cover the theory of generation, how the generation is happening and everything. Then the stability of the generation is the the Sine equation and everything will be covered in the this particular topic. Then transmission. So we are not going to study about the transformers, because transformers are the most important thing in the transmission line. So we are not going to cover transformers. We will be covering more about the transmission lines and the methods of transmitting the power. Okay, and we will be covering a lot about distribution system, and we will be looking at some parts of the loads also. Okay, so these are the important part. You should be careful while you study the power systems. Okay. So now, if you think about India or where we live, so if you look at India, we have 5 grids. Okay, basically known as the grid. Grid is a like something like an infinite bus, what you have studied in your in your machines class or a synchronous machine class. It's a huge area, huge thing where we can get infinite amount of power, or all the small generations are connected to a grid, something like that, where we'll get more maximum amount of energy from a grid or power from a grid, like that. So this concept of grid was introduced in early 1990s by the PSU known as a power grid. So initially the distribution and generation and distribution was localized. If there is one dam there, and that from that dam the energy will be distributed in that particular area. But the concept of grid came in the early 1900s, and the first PSU was introduced as power grid, which now controls the grid. Okay, how a grid should perform and all the things. And if you get a very good gate rank, you can join power grid as an executive engineer. Okay, like all the things. So what are the different grids in India? So different grids are northern grid, then eastern grid, then northeastern grid, western grid, and southern grid. Okay, so these are the different grids basically which is available in India, and these 4 grids is operating at a frequency of, these 4 grids are interconnected in 2006. Okay, in 2006 these 4 grids are interconnected and it is operating at 50 hertz. Okay, and the southern grid is operating at 49.5 hertz. So these two cannot be now interconnected because the frequency is different, right? So it will be an asynchronous interconnection. So then some work has to be done for the next 7 years. Some work has done, and they improved the frequency of the southern grid to 50 hertz. Okay. And now in 2013, Power Grid has joined all the grids together, and they named us one nation, one grid. Okay. One nation, one grid. So that means now all over India, the power system is one. Now, like the whole power system is one in India, like, So if somewhere, somewhere in Uttarakhand or somewhere, sorry, Jharkhand or somewhere, the coal thermal power plant is there, then that power can be now transmitted to the here Bangalore or Kerala. Okay, so that is basically one nation, one grid. So everything was interconnected. So before that, before 2013, like there was a frequency. I already mentioned that there was a frequency difference of 0.5 hertz, right? 50 hertz and 49.5 hertz. So, but there was an interconnection. So that connection was through HVDC interconnection. Okay, HVDC interconnection. Sorry, there was an HVDC interconnection between northern grid and the southern grid. Okay. So I hope you understood what is a grid and what are different grids in India. And now everything is working synchronous mode. Everything is working in synchronous mode. Synchronous mode means now everything is working in 50 hertz. Okay. So I hope you understood. You can just go through the different numbers when it is, because for your interviews they might have ask all these questions. Okay, so these things are very important. Okay, you can just go through the different numbers and everything. Now you can look at the generation part. Okay, right. I will just briefly explain what are the different aspects in India, how our power systems are controlled and everything. So in India, the generation is happening in three sectors. So the different three sectors in India are, first sector is known as the central sector. Okay. So I'll take a new page. First one is a central sector. So central sector are those it is controlled by the central government. Okay, or the PSUs, which is under the central government. So it covers almost about 25% of the total generation in India. The total generation in India, the total power which is generated in India, it is 25% is controlled by the central sector, and state sector, the next is because central government PSUs like NTPC and all other things, NHPC, National Hydropower Corporation, a lot of public sector things are there, and there are some nuclear things also there now. So, and in state, it is 27.8. So 27.8 is under the state, because if you go to all the generating, different state, there are different dams which is controlled by different state. Like if you go to Kerala, you can see a lot of these dams which are under the state government, or the KCB, Kerala State Electricity Board. And if you go to Karnataka also, you can see different things happening. Okay, so this is under 27, and the most of the energy which is generated in India is from the private sector. So don't think the other way, because private sector is having the most generation in India. Okay. So private sector is having almost 47% of the total generation. Okay. So if you look carefully, the private sector is almost having the 50% of the total generation in India. So that means most of the energy coming in India is actually coming from the private sectors. So the private sector basically includes Tata, Adani Power, Tata Power, and all other things if you look at the private sector. Okay. And India has a total installed capacity of 372 gigawatts. Okay. So the total installed capacity in India is 372 gigawatts. So this much installed capacity is there in India. Okay. So these numbers you just remember, because this can be asked in an interview. Okay. So this is the ownership of the energy. Now, if you look at the how these are produced, so there are different plants like thermal power plants. This thermal power plants is almost having 62% of the total power. Okay. So total power generated in India, the 62% of the total power is actually coming from the thermal power plants. And hydroelectric power plants, is giving 12.3%. Okay. So 12.3% is coming from the hydroelectric power plants. Now, nuclear power plant is providing 1.8%. And renewable energy is giving 23.8. Okay. So if you look, the bulk of the power or the maximum power is actually coming from a thermal power plant, right? Because if you go to the the central India like Jharkhand, Madhya Pradesh, and there are a lot of ores are there for coal, and that is the major contribution of power. Because problem with the hydroelectric power plant is that this is seasonal. Okay, this is seasonal. So in rainy season only there will be water in the dams and they can produce the power. Okay. So now the most of the research are now happening in renewables because we have a lot of renewables like sunlight is there, wind is there, tidal is there. So now a lot of research is happening in renewables and there are a lot of research happening in this PV photovoltaic systems or the solar, so that we can increase more production because world is now going to renewable because this thermal and other things are going to end in near future. So we have to convert everything to renewables. So now lot of if we want to continue research in power systems or something, we can actually work in renewable energy systems. Okay. So renewable is the hot topic in this area. And we have a high potential of nuclear nuclear energy, but we are actually, the people are actually very afraid of nuclear because if something happened then it will be a catastrophe, right? So still nuclear has a very high potential, but only 1% of the total power is actually coming from the nuclear. And a lot of research is happening how to make this energy viable. Okay, so you can, if you want, we can actually work in nuclear also to make the energy viable with less problems, and different techniques by which we can actually improve the efficiency of a nuclear or improve the protection of a nuclear, like that. So these are the things you should remember. You should remember, the first thing you should remember is the bulk of the power or the 62% of the power in India is produced from a thermal power plant. Okay, so thermal power plant is the this thermal power plant is contributing the heavy or the bulk of the energy generation. Second is renewable, not hydro. Okay. Hydro is only 12%. And most of the hydroelectric power plants are either in the south or in the north or northeast. In the middle, there are very less hydroelectric power plants. And nuclear is 1.8% and renewable is 23.8%. Okay. So last time, if you remember, before 4 or 5 months, there was something like a thermal, there was a coal shortage was there. So people are expecting blackouts at different regions, but other things actually contributed for that one and make the grid stable. Okay. So these are the important things you should remember because these things they can ask in your interview. Okay. In my case, when I went to Power Grid, they have asked about the different generating stations in India, how it works and what are its contributions. So it was a common tendency that people will say hydroelectric as second because it is not hydroelectric, it is renewable, which work as the second one. Okay, so you should remember this. Okay, I hope you understood the generation part, and these are just numbers. We will be covering this generation again in the other classes. Okay, so you should just remember these things. Okay. Now we can go up to the simple layout, a simple layout of our generating system, okay, or the total power system. The total power system having different components I will draw. So if you look here, this is the generation. Okay. So this is a generation, and so this is happening in a generating station. This is happening in a generating station. So when the generation is happening, what is the voltage level in which we are generating the power? So the voltage level is normally 11 kV. Okay, this is the generating most of the places we are actually generating in 11 kV. So you can ask why we can't go up, because the voltage, if you have to think like this way, voltage always depends on the insulation. Okay, voltage always depends on insulation or the electric field. Okay, so this is very important. Okay. So we have to design the insulation in the machine such a way that the insulation can withstand the generating voltage. So, like we cannot make a very large insulation for the machines, right? So that is a different issue that is basically done by a high voltage engineer. They will decide what is the thickness of the insulation, what we have to make. So ideally they will make design everything for an 11 kV system. Now this 11 kV or sometimes 66 kV. Okay, so this is actually step up to 765 kV. Okay, so next thing is step up is happening at 765 kV. So the next generation is, so this is basically a step up transformer. Okay, so this step up transformer is actually converting this 11 kV to 765 kV, and this is a step up transformer, and this is actually done for transmission. They actually do this for transmission. Okay, so I hope you understood. So now the important question is why we are stepping up for transmission. Okay, why can't we transmit in a low voltage system? Okay, so you should remember this: the transmission is always happening in high voltage. Transmission is always happening in high voltage. So now the question is why? Why is this transmission always happening in high voltage? Okay, you can think about 1 or 2 minutes how this is happening in high voltage. Because if you think like this way, so if the P equal to V into I. Okay, so V into I. So we know that length of the line is constant, so the resistance is now constant. Okay. So if you increase the voltage, what happens? For transmitting a same amount of power, we requires only less current, right? This is very important now, because if we keep the power as fixed, if we keep power as constant, now what happens is that as we going to increase the voltage, this going larger and larger and larger. Now what happens is that the current becomes smaller and smaller and smaller. Then why this current is important now? Because as the current becoming smaller, then the I square R loss becoming smaller and smaller. Okay. That is the I square R, that is the copper loss. Okay. So as the current becoming larger and larger, sorry, smaller and smaller, voltage becoming larger and larger, the copper loss becoming smaller and smaller. So what is the importance of this? That means for transmitting a same power, the line losses are less for high voltage. Line losses are less for high voltage. Okay. So why the line losses are important? Because we are generating some energy here, and this energy is actually coming through this transmission line. Okay. And what if all the energy generated here is lost in this transmission line? Then what is the point of having this, right? So just assume like this. You have something like a water pond here, and you have to transmit this water from here to your home. Okay, assume that your home is here. Okay, so now what happened? So you have to take a bucket or something, and you have to fill the water in it, and You have to actually take the bucket from here to here. Assume that there is a large hole here. Okay, this hole is where the water is lost. Okay. So if you transmit this water from here to here, all the water, if the hole is very, very large, all the water will be actually lost in the transmission, right? No water can reach from here to here. So if you, this hole is basically the copper loss. Basically the copper loss. So as the hole becoming larger and larger, most of the water will be actually flowing into the ground. Okay, that means that these are actually of no use. So you have to make the hole lesser and lesser, or the copper loss lesser and lesser. So that what we can do, we can actually think about increasing the voltage. How we can increase the voltage? So this voltage can be increased by using a step-up transformer. Okay. So what is the advantage of a transformer? So the important advantage of a transformer is that the efficiency is near to 100 or near 99. So that means even if we are increasing the voltage, the energy lost is very, very small. Because if you study the machines thing, the one of the peculiar thing with the transformer is that its efficiency is very, very large. So that means like what is the energy actually happening here or generating here, that is transmitted at a high voltage without any loss in the transmission or in the step-up transformer, right? There will be very small copper loss and core loss. What is happening here? Now you can think about why we are actually stopping at 765. Why can't we go above and above? Like, so that depends on insulation of the system. So, or the insulation of the wire or something like what we are using. Then as the voltage got increased higher and higher, what happens is that the voltage becoming higher and higher, then the electric field also increases near to the conductor. So that may cause us corona and other effects in near to the wire. Okay. So these things are unwanted because the corona causes another power loss in the wire. Okay. And another thing is that assume that there are two lines there and wait. So there are two lines which are carrying very high voltage, right? Like you can say 1 megavolt or something greater than 2 or 3 megavolt. So what happens is that the important property with the transmission system is that the transmission system is always exposed, right? If you think about a machine, a machine is having a yoke, right, on the top. So this yoke actually act as a protective device for the machine. So all the machine, the winding and everything is actually inside the yoke. If you think about a transformer, it is inside the tank. Or if you think about a machine, it is inside the yoke. So that means everything is now protected, all the machines. But if you think about transmission line, so this is one tower, and this is another tower, and the line is actually flowing through this. Okay, like this. So what happens is this is exposed, right? So assume that there are actually two lines actually going parallel to this, right? So there are two conductors like this, and what is the dielectric between these two? That is air, right? So air has something like a dielectric strength. Dielectric of strength is air is 21.2 kilovolt per centimeter. That is between these two 1 centimeter. If the voltage between these two is 21.2, then there will be breakdown happening in air. Okay, that means there will be breakdown happening here. So that can cause a breakdown, so that these two lines will be now touching each other. So this thing is known as a line to line fault. Okay, so this can happen in the air. So that means the property of air to be an insulator is depending upon the voltage, because for all the voltages this air may not be act as an insulator. Okay, that is depending on a particular voltage. So we cannot actually increase this voltage to very, very large, because the air will become basically the air will between the two will actually break down. Okay, so we can do one thing. So if you want to make a very, very large transmission system, we can actually fill the place between these two as some gas which is having high breakdown strength. That is basically SF6. So that is where some very large power substations, we are actually filling the holes inside with SF6. Okay, because SF6 is having a heavy like dielectric strength as compared to air. Okay, these things are actually coming in the protection part. Okay. So you have to remember this. We cannot actually transmit the power in low voltages, because in low voltages current will be very high. So what happens if the current is high? The current is high, then copper losses are high. So that means there will be very high transmission losses. Okay. So we have to reduce. You have to reduce the current. So for like sending same power, if you reduce the voltage, so reduce the current, the voltage has to increase. So we are actually using a step-up transformer for increasing the voltage, and there is a limit for the how much voltage we can increase. Okay, that depends on the insulation of the system, of the transformer and other things, and also depending upon the breakdown strength of the air. Okay, and insulator also there's a creeping, that I will explain later. Okay, about when we study the insulator, we will actually design the insulator such a way that there won't be any single line to ground fault happening through the insulator. Okay, so these things are very important. Okay, so I think you understood what are the important things with transmission. Okay, now we can think how a transmission is happening. Okay, so if you look, the most of the generator, what to generate is always a sine wave, right, of 50 hertz. So there are two important aspects here. If you check here, there are two important aspects. So the first aspect is why always sine wave. First aspect is why always sine wave. Why can't we make a flat top, something like this? Because this is the most easiest one to generate. This kind of a thing, trapezoidal wave. So why are we so adamant about sine wave? We only need sine wave as a generation. We don't need nothing else. Okay. So why are we so adamant that we need sine wave, or we are actually focusing on making it sine wave very very close to sine wave? If you actually look at the power electronic thing, they are actually increasing the number of IGBTs and number of switches such a way that the generated power actually coming from this inverters, or if you look at the power electronic thing, there's a DC is there, and they will use some kind of an inverter to convert this to AC. Okay. So, and they are actually very careful that this should be always sine wave. Okay. So they are switching in such a PWM, pulse width modulation, such a way that it will be always sinusoidal. So why are we so obsessed with sine wave? Why the generation should happen in sine wave? And even if it is sine wave, why we are actually so worried about 50 hertz? Why can't it go to 5 kilohertz or 5 megahertz? Or why can't it go to 1 hertz or 2 hertz? So what is so important about 50 hertz? Like if it is in India, it is 50 hertz. So if you go to Japan or somewhere, it is 60 hertz, and 40 hertz. If you go to US or somewhere, it is 60 hertz. Okay. So only some numbers are there, 50, 60. Okay, right. Like 40, 50 or 60. Okay, why these numbers are so important? 40, 50 or 60. Why these numbers are important? Okay. So the two questions I have posed to you now: why we need a sine wave, and why actually we are actually worrying about this 40 hertz, 50 hertz or 60 hertz. Why are the two things very important? Okay. So you can think about this for a 1 minute, and you can make the answers. Okay, I will explain the answers later. Now we can think about it. Why it should be sine wave? Okay, because it can be a square wave, it can be a trapezoidal wave, and it can be something like that. Okay, so you can just think about it for a minute, and I will be back with the answer. Okay, I think you have thought about the answer. So the first thing is that why sine wave? Because if you think about the different things what is happening in an electrical power system, almost all the things can be modeled as an L and C, or resistor, inductor, and capacitor, right? So that means if you think about a motor, if you think about a generator, or if you think of transmission line, if you think about all the loads, everything can be modeled with three passive elements. These three passive elements, right? So what is the importance of these three passive elements? Because in these three passive elements, if you think about the voltage V equal to L into di by dt, V equal to 1 by C integral I dt, V equal to I into R. Okay. So if the currents if the currents and voltages are sinusoidal, what is happening is, even if you differentiate or integrate, the shape will remain intact. Okay. So that means uh, if you think about, if you make the voltage a sine wave, even if you integrate it, the thing remains same, only with a small phase difference. Okay, like this, the shape will remains constant. If you differentiate it, still the shape will remain constant, because integral of a sine is cos, integral of a cos sine, like integral of sine is minus cos, and integral of cos sine is, differential of sine is cos. That is the only difference is actually coming, because it will either lead or lag the the current, or the voltage, or the other way around. Okay, so that means now we can actually fix the, even if the frequency is same, because we are actually generating for 50 hertz. So if the frequency is same, now we can treat this as a same thing, we don't want to worry about the shape anymore. So that is a place where we consider the phasors. Okay, we can consider this as a simple line with a magnitude, right? We don't want to consider the shape. We can forget about the shape. Okay, because shape is irrelevant if it is sine wave, because integral or differential of sine wave is again sine wave. The shape remains constant. But if you think about a, something like a square wave, okay, so what happened if you integrate this? What happens if you integrate this? This will become a something like this, right? Parabolic curve. If you differentiate this, then it will become something like a delta curve. Okay, so that means we have to now worry about the magnitude as well as the shape also, because the shape got now changed. So that means it's now very complicated. We cannot directly use the phases by like this way, because phasor addition is now very complicated, right? So otherwise, if you think about something like the flat top like this, so here it is straight line. So that means the differential is now constant. Here it will be 0. Now it will be negative and 0 and positive like this. So that means here also the shape is actually varying. So we have to worry about the shape. So the only one curve which gives you exactly the same thing, that is basically sine wave. Even if you integrate or differentiate it, it will give you the same sine wave again. So that means now we don't want to worry about the shape. Okay. So that this is why we are actually doing the phasor. We will make this as V1, V2. We can add these two things together, V1 plus V2. Okay. So another problem will come now, because this is basically a vector addition, right? So is voltage and current vector? Because even if it is not a vector, then how can we add it as a vector addition? Okay, so these are some important questions they will ask you in your interviews. Okay, these are the very fundamental questions. So if you go for some electrical interviews, they will surely ask this question. Even if voltage and currents are phasors, sorry, not vectors, how can we use the property of a vector addition for this? Okay. So one example, so they asked me this question for my interview in IIT Bombay. So there are two wires like this. They kept it an angle of something like 60 degree. So these two wires are kept at an angle of 60 degree. Okay, and this is the resultant. Okay, this is the wire. Another wire is actually coming from here. So this wire has some current like I1, and this current has a current of I2. This is having a current of I2. So what happens if you add these two? So this current will become now I1 plus I2. Right. So this current is now become I1 plus I2. And now what if you change current here and here? So if you actually increase the wire angle between the wire as I1 and I2, right? Will this current change, or is it still I1 plus I2? So that is a question, right? So I will explain the question again in another slide. So you will actually, you won't forget, you will understand the question. There are two wires here like this. So one wire is carrying a current of I1. I'll wait for some time so that this loading process settles. So this is carrying a current of I1. And this is carrying a current of I2. Okay. And some will be actually flowing here, I1 plus I2. So what happens is I just move the wire to here and here. This is now I1, this is now I2. Will this change, or is it still I1 plus I2? Because if these two are forces, right, then this should have changed, right? Because force is a vector quantity. But currents should not change, because even though current has both magnitude and direction, it does not obey vector addition, right? Does not obey vector addition. So that means, since it does not obey vector addition, that means this will always remain I1 plus I2, right? So that means this is not a vector. Current is not a vector, but current is a phasor. Current is a phasor. So some people say phasor is a rotating vector. Okay, these two are just conventions some US people and Russian people used, and some people called it as a vector diagram. And then people start from US start saying, no, these are not vectors. How can you say it a vector? You can have to say it is a phasor diagram. Okay, these are just conventions. Okay, so that means if two sine waves are added like this, then the resultant will be always a sine wave. Always a sine wave with magnitude similar to a vector addition. That's all. Okay, so most of the people always got a confusion whether these two are vectors. That's why we are actually adding it to a vector addition. No, these two are scalars. The voltage and current are always scalar. But the problem is that if two sine waves are added together, the resultant will be always a sine wave, and the magnitude is similar to that of vector addition. That is an coincidence. That's all. Like that, nothing to do with a vector. So it's something like we are adding two vectors together. So we can directly use the property of vector addition. That's all. Doesn't mean that this is basically something happening in a vector quantity. Okay. So you should remember this carefully. Okay. So this is the thing. Okay. So I understood why we are actually considering a sine wave, because why we are actually worrying about a sine wave is the integral is always sine wave and differential is also a sine wave. Differential is also sine wave, and simple vector addition can be used. So you can just take a thing and you can actually check here. So I'll give you as a homework. You can actually check this. check A sine omega t plus B sine omega t plus phi. How these two are added. Okay. So if you can you can consider just expand this sine A plus sine B, or you can actually consider cos or anything you can consider, and then you can add both the things together. At the end, the resultant will be similar to addition of vectors, because the magnitude will be root of a square plus b square plus 2ab cos phi. You will get the magnitude like that way. Okay, so that after like it is similar to the vector addition, which is having a some kind of a phase. Okay, so that will be the answer why we are actually considering sine wave. So if we take the voltage as sine wave, we can forget about the shape, because whatever things happening inside, the shape will be preserved. We don't want to think about the shape anymore. So just assume that to generate a sine wave in somewhere in like in Jharkhand or Chhattisgarh, we are generating a sine wave there, right? So this voltage travels to Karnataka. Okay. So if someone asks you what is the shape of this voltage, because this might pass through a lot of inductance, capacitance, and resistance, right? So still the voltage shape remains sinusoidal, right? We don't want to worry about what all the things is passed. So if it if it was a square wave or it was another kind of a wave, then you have to ask the person why did it pass to an inductor, did it pass to a capacitor, did it pass to a resistor? Then only you can find the shape. Here you can blindly you can say wherever in the world the voltage will be always sinusoidal, because we don't worry about the shape anymore, because even if you integrate it, you differentiate it, the shape remains the same. Okay, you don't want to worry about the shape anymore. So that is the first answer for the first question. The second question is why 50 hertz, right? That is the second question. So you can also think about it, why we are actually considering 50 hertz. Why can't it be something like 0 hertz or 1 hertz, or why can't it be something like 750 hertz? So what is so peculiar about 40, 50, and 60? Is there something? Okay. So this 50 is a British standard. Like we normally follow the British standard because Britishers were here for a long time. So we normally follow the 50 hertz, and this is the basically US people use 60 hertz. Okay. So if you get some like some electrical equipment from US, you can see that it is basically 60 hertz. So today I will cover only the basics of all these things. From tomorrow onwards, we will be starting the exact power systems. Okay. So today the things will be most of the things are the basics. Okay, like what are the important parts, what are the important things like that. Okay, so why we are actually worrying about 50 hertz? So the problem with the like which frequency we have to generate the thing. So it has a history as long as the like as long as the history of the generation. Okay, so at what frequency we have to generate the AC? Okay, so that is a very important question which was there for a long time. So what is the frequency of AC? So there is something, because in earlier days when the electricity was just started, okay, just started to make the things, and like so most of the people use electricity for lamps. That is the most important use of electricity, because to see the things at night. So there was no computer, there was no other things. Factories are very less factories are there. So most of the people use electricity for lamps. So to make the lamps in the like this street lamps and home lighting. These are the two things most of the people used electricity for. So then, if electricity is for lamps, can you think about something which have some impact on the lamps? Okay, so the thing is that just look at a sine wave. Okay, we already fixed that we should generate a sine wave, and next thing is that we have to think about at what frequency we have to generate. So if you think like this lamps are basically similar resistance, right? And the heat generation is the light what we see, so that is I square RT or something, or we can say the heat generator, so it is directly proportional to current. Okay, so that means here the current is actually increasing and reach a maximum point here, then the current starts decreasing. and reach a minimum point here. Since we are taking the square of the current, this will be actually coming here. Okay, the square will be actually, we'll think only about the magnitude. Again, the current is increasing and it is actually falling like this. So what happens if it is given to a resistance? The heat generation will be also like this, or the light is actually produced. So it will look like this. So the current will be increasing. So the light will be increasing, light will be decreasing, again light will be increasing, again light will be decreasing like this. Okay. So that means if the frequency is very small, like what happens if the frequency is very small? That thing is that you can see some bright spot for some time, then you can see some dark spot, then you can see some bright spot for some time and some dark spot. So you can see this practically in the bright lamp method. If you think about a synchronization between two machines of different frequencies, you can see the difference will be very small frequencies, like 1 or 2 hertz, right? So you can see some bulb will be actually getting bright and it will going dark like this. So what is the problem with that? And can we use that kind of a lamp for any practical purpose? No, right? Because for some time it is bright and sometime it is dark. Sometimes it is bright and sometimes it is dark. So then there is a property of our eye, that is our eye can hold the light for or anything for 1/16th of a second, right? We can hold the lamp, like whatever things it is falling in our eye, it can hold for 1/16th of a second. So that means even if it is a light, this light can hold in our eye for 1/16th of a second. That means basically 16 hertz. Okay, 1/16th of a second is basically 16 hertz. So if the light is above 16 hertz, if the light is above 16 hertz, what happens? The light at each instant of time will be kept in our eye for 1/16th of a second. That means even if the light comes down, but our eye, like we are actually fooling our eye. We will keep the things for some more time, right? That means we will get a very good and like something like a very straight light every time, because our eye will keep it for 16th of a second, then the new cycle will come, so it will again keep it like so. At least it should be 16 hertz, right? It should not be less than 16 hertz, it should be above 16 hertz, right? So you can think about this way. This is 16 hertz, so it will store like this. So the next 16 hertz will come and this is already there and the new one will come. So every time there will be light in our eye, right? So it should be something about 20 or 30 hertz. That is the minimum way we can actually keep in our thing. And what is that is the lower limit. So it should not be less than 16 hertz. So this problem is known as the flickering of lamp. Okay, so this problem is known as flickering of lamp. So flickering of lamp was the the important thing by which actually we have decided the frequency of our lower limit of the frequency. So now we can think about the upper limit of the frequency. So what is the upper limit? We can actually fix the thing. Okay, so it depends on the inductance, because there is a transmission is there. So the voltage drop here will be L into omega. So L into 2 pi into F, right? So that means if the F is very large, then the inductance of the transmission line, so the X or the inductive reactance will become very large. That means whatever things generated in a generating station here, whatever things is generated in generating station, it will be actually it will be dropped in this particular inductance, right? That means that is not good. So we cannot actually increase the thing. And another thing is there, P equal to x1 x2 by v1 v2 by x sine delta, right? This is the equation for power flow. So what happens if F increases? So F increases, then X increases. If X increases, then P decreases. That means this is what we are saying, like the transmitted power becoming smaller and smaller, right, as the X increases, right? So that means we cannot actually increase the value of X for a very large value, so that we have to fix the F for some time. So here F should be greater than 16 and f should not be very, very large. So that's why we kept it as somewhere like 40, 50 or 60. Okay. This is the important thing you have to remember. Why we are actually keeping this to thick. And this causes a problem because since the value of f is small, what happens is that x is small. So since the x is small, what happens is that short circuit current is very large. So in our power system, since the frequency is very small, the short circuit current is very, very large, because short circuit current ISC is basically V rated by X, right? Since X is small and V rated is fixed constant, then I short circuit current is very, very large, right? So that's why we have to provide some kind of a protection, right? If the operating frequency is very, very large, then the inductive reactance will almost decay all the short circuit current, right? We don't worry about it. Since we are operating in a less frequency, we have to worry about the short circuit current. And since we have to worry about short circuit current, we have to think about the protection. Okay. So all these things are important in the power system. Okay. So now I will going to explain what are the characteristics of a power system. From all the things what I have said for the last 1 hour, from this actually we can derive what should be the important characteristics of a power system. Okay. So you can think about all these things for 1 or 2 minutes, and you can actually recall this. What are the things I have said? And from this, we will be actually looking at the important characteristics of a power system. Okay, welcome back. So I will just say what are the important properties of a power system. Okay. So what are the important properties of a power system? First property is that the cost of generation should be minimum. Right. Because if the cost of generation is very, very large, then what happens is that much of cost will be reflected on our bill, right? Because if the cost of generation is large, so that will be reflected on our consumer bill, so that we have to pay a lot of money. So nobody is actually gonna pay a lot of money. So we have to make the generation as economic as possible. So cost of generation should be very minimum, and economic load dispatch, right? So assume that there are two places here, place A and place B. So here requires a lot of power, and here we have to require less amount of power. Okay. So we have to transmit the power in that way. We have to transmit the power in economic load. Okay, economic load dispatch. We have to transmit the power, high amount of power here and low amount of power with basically less cost. Okay, that is the thing what should be you have to consider. So generation cost should be reduced. Economic load dispatch you should consider. So these two things we will study in power flow and economic load. So these two things, actually power flow is important to check where we need the maximum power and how we are actually transmitting the power in low cost. And economic load dispatch is used for transmitting the power from one place to another in an economic way. So these two aspects of power of our power system class is actually taken care of these two things. Okay. The third one is reliable power. Okay. That means in India, what we are going to say is we are providing you power at a rated voltage at rated frequency. Okay, so the Power System Corporation or the Power Generation Corporation in India, so they say that we are going to provide you the power in this particular voltage, a voltage, and in this particular frequency. Okay, and this will be seen by the most of the industries in India, and they will make equipments according to this. Okay, so if you think about the iron box or all the motors or anything what we actually use in our home, it has got an voltage rating, right? So this is as specified by the government. So the government is actually specifying this. We are actually, the government will provide you the voltage of this voltage. In India, it is basically for a single phase, it is 240 volt or 220 volt in some places. So 240 volt and 50 hertz, right? This is the rated one in India, 240 volts and 50 hertz. And we are going to say that we will provide you this voltage and this particular frequency. And the power system should be designed such a way that it should always provide this frequency, right, and this voltage. And assume this way, some people are actually designed their device for 240 volt and government is suddenly providing you 260 volt. What happens? The insulation will break down and the equipment will be actually we cannot use the equipment anymore. So here we have to be careful for providing rated voltage and rated frequency. So this is taken care by automatic frequency control and automatic voltage control. Okay, variable frequency control, frequency control and voltage control. So this will be actually, we'll study these things also in power systems, how the frequency is controlled and how the voltage is controlled. Okay, so these two things are also covered in the power system class. So the fourth one is reliable transmission. Okay, so that means the power is generated in the power generating station. This power has to be transmitted from generating station to the load, right? So that transmission should be highly reliable. So in Monday, Tuesday, we will get the power. Wednesday, Thursday, Friday, there is no power. And Saturday, Sunday, again power. Is it a good transmission system? No, right? So we have to study about transmission line and underground cables. Right. So this is very important. So we have to study about how the power is actually transmitting from one place to another, right? So we have to study about transmission line and underground cables, because these are the two places from by which the two things by which the power is transmitted from one place to another, right? So we have to study about the reliable transmission. So we have to study about all these. Then we have to study about the protection, because the transmission system is always exposed, right? So there can be a lot of things happening. So we have to study about relays for protection, and we have to study about fault analysis. Okay, so we have to study the relays, because if suddenly something like a natural lightning has happened, something like a lightning pulse has come, then the relays has to protect this, or some overcurrent has come. So relay has to trip the other systems so that nothing is going to happening in the system. Okay, that is, relay act as a protective device. And if the relay cannot do anything or something like a fault happened in the system, then what we should do? So that we have to think about the fault analysis. Okay, so these two are the important parts. Then we should get a stable system, right? And suddenly something has happened in the load side, so that will be always reflected in the system side or a generating state. Then what happened? So then it is happening so that the system or the generating station should not shut down immediately, right? So then it will be a blackout everywhere. So you have to provide such a way that system will again go to stable. So there we will be studying the stability analysis or the swing curves and everything. Swing curves, then other things like this stability analysis and everything. Then we have to think about modern transmission systems. Modern transmission. That is HVDC and FACT. Flexible AC transmission systems and HVDC, high voltage DC transmission. Okay, so the importance of these two are like these are the modern transmission systems. We can transmit the power in a DC system. Okay, like then we don't worry about the frequency or anything else. Like I will teach you HVDC later. And FACT. FACT is basically flexible AC systems. Okay, so these are the important things of a power system, and we are going to cover all these things in our coming lectures. Okay, like I will be concentrating more on the theoretical part than on the problems. Okay, because that is the most important things for your HL exam and HL interviews. Okay, so you should be very careful with what is basically a power flow or what is basically economic load dispatch and everything. Okay, so these are the important things you should remember. Okay, so I will write in a like the things what you have to cover in the power system. So that is basically the syllabus. So power system syllabus. So you'll study about transmission line, its properties and everything we'll cover. Then cables, then voltage and frequency control, voltage and frequency control. Then we'll be looking at load flow and economic load dispatch. Economic load dispatch. Then we'll be looking at relays and protection. Then we'll be looking at stability. Then we'll be looking at HVDC and FACT. Okay, so almost entire power system is in this form. Okay, so you can actually look at these things for your exam, because power system is very simple things only. Like the thing is that what are the prerequisites for a power system class, because we are going to start the power system like exact power system now. The prerequisites are machines, a bit of machines, a bit of network, and a bit of ultraromantics. Okay, so these things you have to have a good grip on machines, network, and ultraromantics. Then power system is a very simple thing only. Nothing you have to worry, because most of the things are like theoretical ones, and you can, if you know the how a system works, then you can actually predict how it is going to happen. Okay, like these are the important things you have to remember. Okay, I hope you can write all these things now, and these are the things what we are going to cover in this particular session. So we will be having a lecture of 20 hours, okay, total. And most of the lectures I will not be so like worried about numericals, because this 20 hours I will be covering theories and the most important aspects, like which is essential for your technical interviews and technical exams. Okay, so this is the most important part, and you can actually check about the uh, the syllabus. This is the syllabus I'm going to cover. Okay, so I'll be covering a brief introduction about all these things. That's because 20 hours is very less for complete covering the exact syllabus. So I'll be giving you something like the on the top, I will be giving an on the top feeling of what is basically a power system is. Okay. Okay, so I think we can go forward. So the first module is basically transmission system. So we'll be starting with the module 1. So module 1 is transmission system. Okay. So I have already explained that what is the use of a transmission line. So if you think about the transmission system, okay, I'll draw it here so that. So this is basically generating station. Okay. Then there is a step-up transformer is there. Then this way, this is basically transmission line or cable. Okay, both can be. There can be a transmission line or a cable. Then this will go to step down or like the first step down. So if you look at the range, this will be 765. This will be 133 kV or something. And here through another transmission line, we will provide high tension customers. Like for large industries or something. Then there is again another step down is there. It will convert to 11 kV. Then we can give to medium tension customers. Okay. Then again there will be another step down is there. So 11 kV bar 450. Okay. So this is basically our home. So 415 is coming to our home. Or the last one, like household. Okay. So household customers is 415. So three phase is basically 415, and in single phase will be 415 by root. That is almost 240 volt. This is the rated voltage. Okay, 415 by root 3 is rated voltage. So up to here, up to this part, from here to here, this will be a 3-wire system. Like 3-phase 3-wire system. From here to the home customers, it will be 3-phase 4-wire. Because the why we need a 4-wire system is that if you think about a star way, this will act as the ground. So basically each home we need a single phase connection, right? So this will be actually giving from this particular wire. So with respect to ground, we will be actually providing the connections. So in each phase, this will be given to some A, B, C customers. This will be given to D, E, F customers and J, J customers. So these are the very important part. Okay, so like that's why we are in a 4-wire system, because here we don't exactly need something like 4-wire system, because this is only for transmission. Transmission can be done in 3-phase 3-wire system. We don't need an extra wire for this one. But for distribution, we need a 3-phase 4-wire system. Okay. So and there are distribution can happen through feeders. Okay. Distribution happening through feeders. Feeders are two types. There's a ring type feeder is there. Linear feeder is there. And all the things are actually, these things are covered. Okay. I think these are covered in your gauge syllabus. Okay. Like I'm not going to, so, okay. So the things I have drawn here, this red line, this red line, this red line, and this red line, these are basically transmission lines. So basically transmission lines. Okay. So this is why transmission lines are very important here, because between two transformers, or if you think this line, and this line, and to all the lines to home and everywhere, these are basically a transmission line. Okay. So these are basically, so that's why we are going to study the transmission line. Okay. So now an obvious question is why we choose 3-phase. Why can't be 4-phase, 5-phase, 6 or 7? But we can increase up to infinite phase. Okay. So why we stopped at 3-phase? That's a very important question. So if you think this way, so it's a single phase, one phase. Power is VI cos phi, right? The two-phase, there are two-phase systems are there in the world. Okay, lots of places are there, and two-phase furnaces are there. You can think about a Scott connection. It will convert a three-phase to two-phase. That is basically root 2 VI cos phi. Then three-phase power will be root 3 VI cos phi. So if you increase this, so it is one. So like if I draw a curve of power with respect to phase, so one phase is basically 1 VI cos phi. That will be 1.44. That will be 1.732, like that. So as the power increases, the effective, as the phases increase, the effective increase in power is very less, right? It is almost saturated to something like 2 volt, 2 VI cos phi. Okay. So there is no point in increasing it above. So the fourth will be almost like 1.7, this 1.73. So if you add one more, it will be 1.75. It will be one more, it will be 1.78, like that. So it is almost like a saturation curve. So there is no point in increasing above this particular point. So that is basically three-phase. So that's why we actually fixed it to a three-phase, because the gain what we are getting by increasing the number of phases is not relevant. Because if the number of phases is large, we have to draw one more line, right? So three-phase, three conductors are there. Four-phase means four conductors should be there. Five-phase, then we have to get one more conductor. Six-phase, we have to get another conductor, like that. So that is very difficult. So there is no point in having this kind of a connection, right? Because we have to spend a lot of money in buying these conductors. So that's why we are actually stopping our increase in phases to three-phase. We are not thinking about four-phase or five-phase or six-phase. Okay, because the increase in power output is irrelevant after three phases. Okay, so that's very important. So what are the important characteristics of a transmission system? What are the important characteristics of a transmission? Okay. So the first characteristic is it should carry power, right? So transmission should carry power, and it acts as a branch in the network. Where bus act as a node. Okay. So what is basically a branch? A branch connects two nodes, right? That's why transmission line connects two buses. Bus 1, bus 2. Okay. The power flow from one bus to another bus is happening through a transmission line. Okay. So that's why this is very important. So the power is actually coming from bus 1 to bus 2. Then resistance of this should be small. Why the resistance should be small? Because the resistance become large, then the transmission line losses will be large. Line losses becoming large. So that's why that problem is, that is efficiency comes down. Okay, so that is very important part. The line loss should be small so that the efficiency of the transmission should increase. Okay, so if you think in a general scenario in India, almost 40 to 50% of generated power is actually we are losing it through as line losses. Okay, so almost half of the power actually we are losing is at line losses. So that's why we are actually planning to upgrade the voltage levels, so that almost everywhere in India the voltage level is going to upgrade in the near future. So that now also there are extra high voltage transmission lines are now available. So the line losses are now we have to reduce it. Okay, so this is very important. So you have to increase the transmission system capability of transmission system. So just think like this. And resistance should be small, and this transmission system or transmission line should be made of metals, right? Why metals? Because metals have a very low resistance. So transmission system should be made of metals having very low resistance. That is, we can think about aluminum, copper, silver, gold, right? These are the things which are having lesser, having less uh, resistance. So we can just forget about these two, silver and gold, because you know it, right? Because assume that in our place, the transmission line is there, and this is made up of gold. How it will be? Like next day, people will come and cut the gold and they will take it away, right? Because that is not going to be a viable option because the cost of the gold is very large. So, and gold and silver. So the next possibility is aluminum and copper. So from this, we actually choose aluminum, right? Because aluminum having some important properties. These properties are very important because they will ask you in question in interview why you are choosing aluminum instead of copper. Okay, the first one is lightweight. The weight of aluminum is very small, okay, for a fixed volume as compared to copper. Then abundance. It is available like in a lot in earth. Then low cost. Okay. Then less corona. Okay. I will explain this corona and things later because this aluminum conductor will have less corona. That is happening due to resistivity of aluminum is greater than resistivity of copper. Okay, we are saying that the resistance should be small, but this resistivity of aluminum is bit higher than resistivity of copper. So that means for transmitting same power, the aluminum conductor should have a higher cross section area than compared with a copper, right? So that means we need a bit more oleum of aluminum in comparison with oleum of copper, right? So that means oleum of aluminum should be greater than oleum of copper. So that means the radius is now increased so that the corona, or if it's other way, if the radius is increased, then electric field is now decreased because electric field is actually depending upon the surface radius. Electric field is now decreased so that corona is also decreased, right? Corona depending on electric field. So at the edge, the electric field will be very small in comparison with that of a copper conductor, right? But we need more aluminum in comparison with copper, but the cost of aluminum is so small, so again it is actually viable, right? Now the next question you can think is why actually we are considering only circular conductors. So everywhere if you go, our wires are actually circular, our transmission system is also circular. Our actually the everywhere if you go, the transmission thing is happening uh, through a circular conductor. So why is it so? Why can't we have a rectangular conductor? Why can't we have a triangular conductor or trapezoid or something like a pentagon conductor? Why we are actually focusing on circularity? Okay. You can just think about it for a minute and you can actually think about why all the conductors are circular. Why can't this be rectangular or why can't this be triangular or something else? Okay. So that is very important thing you can think because this is very important. Okay. These things they can ask you in your interviews. Why we are actually thinking about circular conductors only. Okay. So why we are considering a circular thing is that, so assume that we having a rectangular thing. Okay. So we have a something like a rectangular conductor. So that means there are four edges here, right? One edge is here. Just wait for something. This is another edge. Okay, there are four edges. I think you can see the four edges there. edge 2, edge 3, and edge 4. Right. So that means these edges having very sharp points. So if we zoom this, we will get something like this. Right. So this will become a very, very sharp point. That means the electric field at this point is very, very large. Right. So what happens if electric field is very large? So if electric field is very large, then what happens is that the near to the edges, the air will get ionized. So since the air will get ionized in the nearby electric, near to the edges, then what is happening is that the air will have corona effect. So if you think like this way, seems like something like a needle. So you can see some kind of an arcing effect happening near to the needle, right? If you give a voltage here. So similarly, you will get 4 different places where you will get an arcing effect. So if you think about circles, there are no edges for circles, right? Like so that the electric field will be distributed uniformly across the surface of this conductor, so that there won't be any arcing effect or corona effect. Okay. So arcing effect or corona effect. There won't be any arcing effect or corona. That's why actually we are considering circular cross section conductor. Okay. Now we can think about rating of transmissions. So these are some of the very important part in the transmission system. What are different ratings you have to consider? The first rating is voltage rating. Second one is current rating. And third one is power rating. So voltage rating is basically V line to line RMS. Okay, in some question, if they have given you a for 765 kV 3-phase transmission line. Okay, that means between any two line, the RMS value of the voltage is 765 kV. So if you want to find the voltage of this with particular ground or with respect to neutral, then you have to find 765 by root 3, right? So all the voltages will be in line to line RMS, right? So all the voltages will be in the line to line RMS. So if you want to find the phase, you have to divide it by root 3. So voltage will be always specified in RMS values. Okay. Voltage will be always specified in RMS values line to line. The current will be always specified as I line. That is the line current. Okay. In normally we consider the transmission system as star. Doesn't mean that it should be always star, but unless specified, we consider it as star. Okay. And the line current will be equal to the phase current. So unless it is specified as delta, we should consider it. If nothing has been specified in the question, then take it as star. That is a normal standard procedure. Okay. So this will be V line to line. This will be I line, comma, I phase. Both will be same. Okay. So the power will be root 3 V line into I line. So this will be the power. Okay. So don't forget these things, because this is the rating, because I am not going to say this again in some other places, because unless specified in the question that voltage is basically phase, otherwise the voltage will be always line. Okay. So that is basically important. I hope you understand the question, understand the concept of okay. Now we can think about what are the different classification of transmission line. You can wait for some time so that the saving of the other slides. Classification of transmission. Okay, the first classification is basically depending upon the voltage. This is high voltage transmission, because transmission is always happening in high voltage. Okay, distribution is always happening in low voltage. So we have in power system, we have to study about the high voltage side, that is the transmission side, and low voltage side, that is the distribution side. Okay. High voltage transmission. That range is 11 kV bar 33 kV. Okay. These two above 11 kV, we consider this as high voltage transmission. Second one is extra high voltage transmission. So extra high voltage transmission is happening is 66 kV, 132 kV, and 220 kV. This is in extra high voltage transmission. Then third one is modern EHV, modern extra high voltage transmission. That is in the range of 400 kV. These numbers you have to remember. And the fourth one is ultra high voltage transmission. That is happening in 765 kV. So these things you should remember. What are the classification of the transmission system? Okay. Now we can think the classification of distribution system. First one is the primary distribution. So the primary distribution is happening between 11 kV and 33 kV. Okay. So above 33 kV, this will be extra high voltage. Okay, the distribution, primary distribution for the high tension customers, it is happening in 11 kV and 33 kV. And secondary distribution is going to happening between 415 and 220. Okay. These are the normal 3-phase for some industries and 220 for homes. Okay. So these are the distribution. This is the primary transmission. This is for primary. This is for distribution. Okay, so you should be careful with this. Okay, because these numbers they can ask for the exam. Okay, what is basically primary distribution? What is basically secondary distribution? So these you should remember all these things. Okay. So by this, I hope we can actually stop for today, and we can actually in the next class we will be actually starting with the transmission lines. So the next class we will be starting with transmission line. So in transmission lines, what we are going to cover is different types of transmission line. That is based on this geometry. Then based on the length. So geometry means single strand, multi-strand, composite strand, bundled conductor. Based on length, it will be small transmission line, medium transmission line, and a large transmission line. Okay. So that is basically important. Then types of different types like hollow conductor and bundled conductor, and all these things will be covered here. Then different types is there. Then we'll be looking at inductance, capacitance, and resistance of the transmission line. This is very important part. Then we'll be looking at the frequency thing, that is Faraday effect, another kind of a thing. Faraday effect, and that is basically related to the high frequency or the large transmission lines. Okay. So these things we'll be covering, and we'll be looking at something related to the cables. So why cables are there? What is the this cylindrical cable? How to find the electric field inside a cylindrical cable? How to find the capacitance of the cable? How to find the inductance of the cable, like that. All these things will be covered. Then three-phase cables, like three-phase cables are there. Then how the cables are constructed, what is the geometry of the cable, and all the things will be covered in the transmission system. So by this, the first part will be over. So most probably by the next two classes, the transmission part will be over. Then after that, we'll be going to look at the economic things, that is load flow and economic load dispatch and other kind of things. Similarly, in 3 or 4 sessions, we will be covering whole in total 20 hours maximum. 20 to 30, 20 hours is the one. So we will be covering everything in the next few hours, okay, next few sessions. So by this, we can read about all these things. Where will you come for the next session? Okay. So by this, we are going to end today's class. I hope you understand the things. You can give a feedback of the class to this one. And so in next class, I will be doing some numericals also, like small questions I will be adding here, and you can actually look at that part. Okay. So that part also you can actually cover. I will doing small questions in the next part. Okay. So by this, we are actually going to end today's class, and because as you think about power system, power systems are like one of the most important part in electrical engineering. So if you think the core electrical engineering, if you think there is machines, then power electronics, power systems, network, control, and analog. Okay, control and analog. So these 5 chapters, or this source 5, not 6 analog. Okay, so this will be actually contributing about 80% of the total electrical. Okay. So almost 80% of the question you can get from these 6 subjects. So these are the core basic subjects in the electrical engineering. So you should be careful with this. And any exam of electrical engineering subject, if you are going to write the examination, then you should be you should be clear with the 6 subjects. Because even when I was also preparing GATE, I just did for these subjects plus engineering mathematics. So you will get approximately 70 to 80% of the marks, and that is more than enough for you to qualify the examination. Okay, but make sure you studied it perfectly. Okay, this one: analog, machines, power electronics, power system, control, and network. So these 6 subjects are very important for all the examination related to electrical engineering. So you should be careful with this. Okay, so by this, I'm going to end the class now, and we can meet in the next session where I'll be actually looking at the transmission line. Okay. Thank you for your kind listening. It's almost 1 hour and 45 minutes. From next class onwards, we will go up to 2 hours. Okay. Thank you.